Okay, so our next topic is discussed in Friedland in Chapter 6, Full State Feedback Design. Now, the slides I'm going to discuss now is really a combination of slides I've previously used when I was using Tawari and other slides that I've used even earlier with Friedland. And because of that, I'm now introducing this convention of indicating the equation numbers with a capital F if it's an equation from Friedland and a capital T when it's an equation from Tawari. Now, to introduce this, consider a plant in the standard state space form as we have it in these two equations, the state differential equation and the output equation. And let's consider the suggested control law that the input vector u as a function of time is the negative of some other gain matrix G to be determined post multiplied by the state vector X. Now, if we substitute this control law back into our equation of at the top of the slide, the plant equations, in other words, this u is then replaced by minus gx and also the u in the output equation, it leads to these two equations. You need to realize that this describes a so-called regulator. A regulator, you can think of a regulator as a control system without an input. In other words, the regulator will have dynamics only if it's disturbed, if you perhaps start with some other initial conditions. The regulator, since it doesn't have an input, it also doesn't have a particular solution. It only has the homogeneous solution. It's like the differential equation with a, remember, if I take this term on the right-hand side of my differential equation to the left-hand side, I have a homogeneous differential equation. There's no excitation. So the whole dynamics is just the homogeneous solution. So regulator design is described in I think this is Dorf, number 2, number 4. I cannot remember what is the reference for, is Tawari. So it's described in Dorf and Tawari also. But certainly in Friedland, he then has this whole section about the regulator design. Let's just look at the block diagram of a regulator. This is the block diagram of the regional system at the matrix level, right? There are the two equations that we started off, and this is the block diagram representation of these equations. So if I then build a regulator, it means basically I take the state vector, I then pre-multiply by minus g, and I set this equal to the input. So now you can see with this, I have this system. It still has an output, but it doesn't have an input. Okay, so this is a regulator. Okay, now the interesting thing is, it's claimed that we can place the K system poles wherever we like, provided that the plant is controllable. And this is referred to as pole placement design. It's actually, in a certain sense, strange that it's called pole placement design, because it's a design method that's unique. Well, when I say this, I need to qualify this a little, but I'll qualify it in a moment. I'm claiming it's unique to the state space method. It was something that did not exist before state space methods were introduced. If you think back of classical control theory, the purpose of design is to change the system dynamics to be more favorable to what it is without the control system. So with classical design theory, if you think of something like the root locus method, remember the root locus diagram is a diagram on the complex S-plane of where the poles of the system are located for various K values, where K is the gain in the loop. So for various loop gain values, the poles of the system can vary in the S-plane, but only along the root locus diagram. So if you think in terms of classical control theory, I can say I can place the poles anywhere on the S-plane. Of course, there are certain areas in the S-plane where it's more beneficial to have the poles than at other places, right? So I can claim I can place the poles on the S-plane wherever I like, provided that they are located on the root locus diagram. That is what classical control theory tells us. And so when state space method was introduced, then the state space method says, no, but I can actually place the poles anywhere on the S-plane, wherever I like. This is in a certain sense the power of the state space methods, the fact that I'm not limited to just the locations of the root locus diagram on the S-plane. But the reason why I think it's a bit funny is called pole placement. Strictly speaking, the state space method is a time domain method. It doesn't know of poles. It knows of eigenvalues of the A matrix, right? So when we talk of pole placement here, we're really talking of the eigenvalues of this new A matrix. Please note that this is now my regulator state differential equation. So essentially my A matrix now is not the original A matrix, but it's A minus BG. And of course, B post multiplied by G gives me a matrix of the same order as a square matrix, the same order as A, otherwise I cannot subtract the two. So this matrix A minus BG is a new A matrix of the regulator, of the closed loop system. And what I'm talking about when I say I place the poles, it's really not pole placement, it's eigenvalue placement. I can place the eigenvalues of my closed loop system, of my regulator, the eigenvalues of A minus BG anywhere on the S-plane. Now, to be fair to the classical control theory, when I said just now that you can place the poles anywhere as long as it's on the root locus diagram, of course that argument is based on a single feedback loop with a single gain. And to be fair, that's not what we're talking about here. Here we're talking about feeding back all the state variables. It's not a single variable, it's all the state variables that are fed back, and all of them multiply with gains. So you may have a multitude of gains here, the whole matrix of gains. So that is essentially what causes the difference. It's not the single gain, it's a large number of different gain values that gets multiplied in a feedback loop with the state variables that are being fed back. Perhaps I should just, to refresh your memory, go back to this slide. So you see here, I'm feeding back not a single variable, I'm feeding back all the state variables. And if I've got a single input case, if used just a single time function, a scalar time function. In other words, if the B matrix is a column, in that case, this G is a row vector, and the number of gains in the G matrix is just the same as the order of the system. In other words, if the A matrix is 4 by 4, I'll have 4 values, 4 gain values. But if B, for instance, is a 4 by 2 matrix, if I've got a fourth order system, A is 4 by 4, but I've got 2 inputs, then B is 4 by 2. In that case, G is 2 by 4. Then I've got 8 gain values that I can play around with. So it is perhaps not a 100% fair comparison to compare the root locus diagram with the pole placement that I'm talking about here. It's altogether a different approach, so perhaps one shouldn't really compare the two. But I'd like to do the comparison just to perhaps give you an indication of how does this now differ from something like a root locus diagram. Well, it differs because we really have the option of placing our poles anywhere on the S-plane. So we can really create the system that we'd like in a certain sense with this pole placement technique. Let me just qualify also, I said that it's available only in state space methods. it is true that after it's been introduced, this notion of being able to place your poles anywhere on the S-plane, after this notion has been introduced by the state space methods, the people that prefer to work with classical control theory also expanded the classical control theory. So I believe that currently or nowadays there is actually similar techniques available in classical control theory where you can actually also place poles anywhere in the S-plane. But it's something that came later. It wasn't at the time when the state space methods were introduced. This was a new idea of being able to place your poles anywhere. Okay, so let's investigate that further. Friedland, when he discusses this, limits himself initially to the single input, single output system. And so after he's introduced this limitation, he then treats it in, I would almost say, minute detail in section 6.2. And I'd like you to work through this. Try to understand this. Because it's really at the heart of this whole approach. It's perhaps described in a little bit less detail by Tavari also in his section 5.3.1. Now, I'm going to just sort of skim over what Friedland does in my presentation, but I am following what he's doing, so I'm also here mostly following his notation. Consider once again the regulator state differential equation obtained by closing the loop around the plant with a control law U is equal to minus Gx, written in this form. Now I can write this as A sub Cx, where A sub C is, the sub C indicates the closed loop. So this is the closed loop A matrix, which is A minus Bg, something that I've mentioned already a little while earlier. Now, since we have a single input system, the B is merely a column vector, and because of that, Friedland then changes it to a small b. He has the notation that he always uses a small letter for a column vector, and for the row vector, then he simply writes the transpose of that, the transpose of a small letter. Now, because the B matrix is now a column vector, it means that the G matrix, for this to be able to happen, for this multiplication of BG, it means that G must be the capital G must be a row vector. And so he then writes this row vector as G transposed, namely G1, G2 up to GK, where K is the order of the system. Of course, it means that G without transposed is then a column vector. G1, G2, G3, G4, one above the other. Okay. So it is now our goal to determine the K unknown gains GI. In other words, for now, these elements in the G transposed row vector is still unknown. We need to determine this. And in doing so, place the K poles of the closed loop system at the S-plane positions where, at the S-plane positions that we choose. Or another way of saying this is the eigenvalues of AC on the complex eigenvalue plane. Now I've put a link in here to, I think, the block diagram. So it's really the closed loop poles of this system that we'd like to, or the poles of this system, which is now a closed loop system through this control law. This is the control law. And we'd like to select the elements, the K elements of this G matrix, which is really a row vector, in order to place the poles where we like them to be. Now, I've written, or Friedland has written, the regulator state differential equation now in the slightly different form. We now use the small b rather than the capital B because it's a column vector, and then the G transposed to indicate that G itself is also a column vector, or G transpose is a row vector. Now, to determine the gains G, we set up the characteristic polynomial of the closed loop system. And of course, that would be the determinant of SI. I can now use S, the Laplace variable, or I can use lambda as the eigenvalue variable. But so since we know that there is this correspondence between the eigenvalues and the Laplace domain poles, it's perhaps fitting to then use S rather than lambda. So the characteristic equation of the AC matrix will be the determinant of SI minus AC. Okay, everybody happy with that? That's how the eigenvalue is defined. The eigenvalue of a matrix can be calculated by solving the characteristic equation, which you get when you calculate the determinant of the eigenvalue variable times the identity matrix minus the matrix itself. Okay, so and if you do this, you'll get the you get the characteristic equation in this form. It will be a kth order polynomial in S in the eigenvalue variable with coefficients. And for now, you can think of these coefficients as unknowns: a bar 1, a bar 2, a bar 3, up to a bar k. In other words, I've got, in this polynomial, I've got k plus 1 terms, but I can always divide the polynomial through the coefficient of the highest order of S, so that the coefficient of S to the power of k is 1. And then I'll have, remember I've got k plus 1 terms, but then I've got k coefficients in the polynomial. Everybody happy with that? Now, these coefficients, if you now think of how you calculate this characteristic polynomial, these coefficients will be nonlinear functions of the elements of G. Remember, you calculate this determinant, but the G's are unknown values, like G1, G2, and so on. And so if you calculate the determinant in the way that it was first introduced, when the first time you calculated the characteristic equation, you'll find that these coefficients are all functions of G, but it's nonlinear functions. Some of these coefficients, for instance, may be the sum of all the G's. Some of them will be products of, some of them will be second order terms, products of, let's say, G1 with G2 and G3 with G4 and G1 with G3, all the different permutations. Some of them will be third order, will be G1 times G2 times G3 plus, for instance, G4 times G5 times G6, but also all the permutations of combinations that you can think of. So it's rather simple, but it's also quite complex because it's nonlinear functions of the G's. But on the other hand, the moment that we've selected the pole locations, these coefficients are no numerical values. Why do I say that? Well, the moment I've selected where I want my eigenvalues, I can reconstruct the characteristic equation from those eigenvalues. The characteristic equation will simply be S minus the first eigenvalue between brackets multiplied by S minus the second eigenvalue plus S minus the third, multiplied by S minus the third. In other words, it's, if you have the poles of a system, you can reconstruct the characteristic equation by simply multiplying for each pole S minus the pole value. And if you multiply that together with over all the poles, you also have the characteristic equation. And if you do that for numerical values of the poles, you'll get a polynomial with known numerical coefficients. So in doing that, the A1 bar, A2 bar, A3 bar, etc. are actually known numerical values for a certain selection of the pole locations. Okay, everybody happy with that? So this means that doing that renders k-simultaneous nonlinear equations in the k unknowns, the elements of G. In other words, I can, well, this first term doesn't give us any equation because it's just 1 is equal to 1. But if I look at the second term, the A1 bar is a known numerical value after I've calculated the characteristic equation from the chosen pole locations. But I also have an expression for A1 coming from calculating the determinant of this matrix with the unknown G's. So this gives me a nonlinear function of G being set equal to a known numerical value. And the same applies to all of the coefficients. So all k coefficients here gives me then, each one of them gives me an equation where I've got a nonlinear function of G, of all the G's, being equated to a known numerical value. So I've got k simultaneous equations that I can solve for the unknown G values. So it's very easy, it's just doing that. And then doing that, once I've solved those equations, I've got the G values, the gain values that if I plug it into the system, into this block diagram of mine, I'll have a closed loop system of which the poles are located at the locations that I've selected. Or in other words, where the eigenvalues of the closed loop A matrix are located on the eigenvalue complex plane at the locations that I've selected. Okay, so I'm claiming it's very easy. It's not really so easy. It's quite difficult when to solve when the order of k is large. In other words, if you have a 2 by 2 system, if the A matrix is 2 by 2, it's actually possible to do this. If it's 3 by 3, it's perhaps still possible to do it. If it's 4 by 4, well, it's going to be a little bit of a pain, but you may still be able to do it. If it gets 5 by 5 or 6 by 6, it becomes much more of an effort. Of course, it also becomes easier now with the fact that programs like MATLAB and Python has symbolic manipulation available. So you can use that. So it's certainly a valid approach, but it is tedious and perhaps very difficult when the order of the system is large. So this is not really the approach that we would like to follow. Okay, so maybe I should make the break here, and what I'm going to do next, following Friedland, is to show that there is actually some alternatives to following this approach of solving these nonlinear equations simultaneously. And so let's make a break of 20 minutes. It's 10:05 now, and so I'll then reconvene at 10:25. Is that fine? Give you a chance to have a cup of coffee. I'm going to lock the door here, both doors, so you can leave your stuff here if you want to. Oh, and I must stop the recording.